I'm Robert Young. I am from Force Performance. We've been building turbos for a while. A lot of y'all probably might know me or maybe not know me, but I started doing turbos in 1990, 95, 96 at a place in Houston. It was a diesel truck shop. And it was a lot of fun. The first thing I realized was, wow, you don't have to build these the way that they come. You can mix and match parts. And so I did. And that led to all the Frankenstein series of turbochargers that we did for the DSM in the 97, 98, 99 period. And that led to the green and the red models for the DSM. And if you've been doing DSM turbos for a while, you're probably familiar with some of those turbochargers. That was a good time for us. Inherently MHI based, but so a lot of people kind of know me as a Mitsubishi Heavy Industries turbo kind of guy. But a turbo is a turbo, just like a toilet's a toilet, and if you can work on one of them, you can work on the rest of them too. So we ended up branching into a lot of things. They're doing diesel turbochargers now, Chevrolet LS focused turbochargers for the big LS craze that's happening. Don't ignore $500 junkyard engines with $600 turbochargers on them. They'll surprise you. Okay. So that's a little bit about me and what I'm kind of about, and if you're just not familiar with me, there's that. In addition to that, the main thing I wanted to talk about, at least the talky part of this before I go to the question part, is I want to talk a little bit about turbocharger seals and leaking a little bit. If anybody that has turbocharger has had smoke come out of their tailpipe, we just saw the 8.0 car, the multicolored one, just make a pass. And what happened when he got to the top of the track? He lifted and smoke came out. Why does that happen? Is the motor broken? Is the turbocharger broken? Why did that happen at the top of the track? Who would think that they understand why that's happening at the top of the track when you lift? Okay. Yeah, so there's a lot going on, right? You know, what's the prevailing trend there, okay? Well, the prevailing trend is the fact that as he's going down the track, he's running 30, 40, 50, who knows how many pounds of boost pressure. He's probably running some sort of alcohol or methanol-based fuel, which is a really cool burning fuel. It doesn't get the piston really hot. You generally have a lot of bore clearance, piston to wall clearance on an engine like that. You're gonna get blow-by past the piston, especially at this boost pressure. You think, oh, it's a cast iron block, it's not moving, it's moving. I promise you it's moving, you know? So as it's moving and wiggling and torsioning and vibrating, air is leaking past the rings. It's filling the crankcase up with some pressure. By the time he gets to the top of the track, he might have 2, 3, 4 pounds of crankcase pressure building up, depending on how adequate or inadequate that vent system is for his crankcase, and whether or not he has a vacuum pump or a scavenge stage or anything like that that's sucking on the crankcase. There's a lot of benefits to having crankcase vacuum. I won't go into that. That's more of an engine topic. But what's happening, you get to the top of the track and you got 50 pounds of intake manifold pressure, you got 50 pounds of turbine pressure, and you got 5 pounds of crankcase pressure. And when you lift the throttle, the boost pressure goes to 0 instantly. The exhaust pressure goes to 0 instantly. But what about the 5 pounds of crankcase pressure? It's got the smallest tubes connecting to it. There's just a 1/2 inch tube here and a 1/2 inch tube there connected to a valve cover. Nothing's connected to the bottom of the motor where the pressure's coming from. Okay, so the bottom of the motor where all the pressure's coming past the rings and filling the crankcase, there's oil mist there. You got pressure blow-by coming past the pistons. So you got a big tornado of oil mist in there. There's 5 pounds of pressure in that, and all of a sudden there's no more pressure in the exhaust manifold or the intake manifold. Well, those are connected to the turbo housings. So there's no more pressure in the turbine housing or the compressor housing, but there's 5 pounds of pressure in the bearing housing. So it takes about half a second or so for that 5 PSI in the crankcase to bleed off when you lift at the top. So for that half second, there's 5 PSI inside the bearing housing, there's no pressure in either housing, and there's about a 20 to 50 cubic feet per hour leak rate past these seals in this turbocharger. So in the half second that was there, some quantity of air, about like this big, went out past the seals, okay? And where did it come from? It came from the bottom of the motor. The oil tube is connected from the bottom of the turbo to the crankcase. Bottom, not where you're venting from the valve cover. Tornado of oil mist in there, so we're 5 pounds of pressure in there. For half a second, that 5 pounds of pressure spits backwards out like a shark through the turbine, to the turbine seal and the compressor seal, okay? And you need to go change your shorts now. That's what that puff of smoke is at the top. Now, how do you make that not happen? Vacuum pump, scavenge stage, PCV valve. Oh, we hate those. Get those the heck out of the motor, right? I don't want a PCV valve. That's emissions. I hate the EPA, right? Oh man, terrible. No, we love the EPA. We love PCV valves, okay? Because when that dude got to the top of the track and he lifted, he had 20 pounds of intake manifold vacuum. And if that 20 pounds of intake manifold vacuum was connected to that catch can, what would have happened? That 5 PSI in that crankcase would just poof, instantly. Faster than it could shart out through the seals, that crankcase pressure would have got sucked into the catch can by the intake manifold, and it would have just been something that needed to be drained out of the catch can instead of a cloud of smoke at the top. Spark plugs wouldn't be fouled. He'd be able to read his plugs better. You know, it's just been an all around better deal, you know, at the top there. So piston ring seals, what the heck is that, and why can oil shoot out of it? Well, we've all seen piston rings. They're on pistons. They're also on turbo shafts. So in a piston, the ring is shaped like this, and the piston goes up and down, and there's a gap on this side, and it goes up and down. And blow-by goes through the gap in the ring. That's how you get the crankcase pressure. And the turbocharger, we don't have a shaft that goes up and down. We have the shaft spinning, but we have the same type of seal there. It's a gas seal. So it's got side clearance on both sides. It's a groove on the shaft. The ring fits in the groove. It comes to about 4 6/1000ths from touching on the end. Okay, so there's always a leak there. People say my turbo leaks. I built it that way. It's supposed to leak. Okay? Yes, I know. But it's always supposed to leak from the outside into the inside. Okay? It's always supposed to be some boost pressure leaking past the compressor seal into the cartridge, some exhaust pressure leaking from the exhaust housing through the turbine seal into the cartridge, adding to that crankcase pressure that you need a vacuum pump to suck out, or a PCV to suck out, or a big vent to suck out, or vent out. So when you have a piston ring seal, so I'm no longer going to model it as a piston ring. I'm going to model it as a wall with a tiny hole in it. Okay. On this side, I have the crankcase pressure through the oil drain tube, the crankcase. So this is inside the bearing housing. This is the turbine housing. But there's a tiny hole here. And exhaust gas is supposed to leak into the bearing housing. Boost gas is supposed to leak into the bearing housing. It's controlled and it's metered, and so you know how much it is. It's a controlled amount of leakage, but it's from the outside to the inside. That's the pressure differential. That's called a positive pressure differential. We always have more pressure outside in the housings than we do in the bearing housings, so the leak's always from the outside to the inside. But when you invert that pressure differential and you have 5 PSI pressure inside the bearing housing and you have no pressure in the end housings, now you're leaking from the inside out, but it's consequences, okay? There's no oil in the exhaust gas. There's nothing in the exhaust gas that bothers the crankcase, but if you take the crankcase gas and you vent it into the end housings, you have brought oil with it, because that's a tornado of oil going on in there. The crankshaft's going around, there's counterweights, there's oil flying off of everything, off the crank. There's a windage tray in there trying to deal with it, but it's not working. And it's just oil everywhere. So as soon as that 5 PSI happens, and then you invert that pressure differential, the gas comes out of the bearing housing and into the end housings, and just for that split second, it just out past the seals, and you have that smoke on the top end. So anytime, and you can do that in a variety of ways, not just lift at the top end, but you can just be driving down the road and decel down a hill. And do the same thing. If you don't have the PCV in place that's drawing a vacuum on the crankcase while you're decelling, you can end up with more crankcase pressure than you have end housing pressure, and you have oil coming out of the turbocharger. Before we move on to anything else, does anybody want some clarification on any part of that little explanation or that little diatribe there?
So does it make a difference if you're venting into the intake pipe or PCV or into the intake pipe through a man hose?
Yes. So you will, any vent that goes into the intake pipe for the turbo, that's your wide open throttle crankcase pressure control. Okay? So while you're on wide open throttle, there's vacuum in the inlet of the turbo. There's a pipe that goes to a filter typically. There's be vacuum in that pipe. While you're on boost, that's your vacuum source for the crankcase. So the intake pipe goes to the catch can, which would be closed, okay, and then to the motor. And the PCV is closed. So you have a PCV and an intake pipe. So the intake pipe sucks on the catch can while you're on power, and the PCV sucks on the catch can while you're off power, while you're lifting. Those are your two modes of having crankcase pressure evacuation or vacuum on your crankcase. While you're on power, you have opportunity to draw on the crankcase with the air intake, but you gotta baffle really well because you don't want to bring oil into the charge area, okay? Because that's going to be a detonant, and you're gonna detonate by having oil mist in there. So really effective catch cans are important for that. So you want your intake pipe to suck on your really good catch can that has really good baffling in it while you're on power, and then when you're off power, you want the PCV to open and suck on the catch can too. It's also same baffling, so no oil's going into the intake manifold then either. And you just slowly accumulate oil in that catch can.
So do you run a second can for that then? Just a dedicated one to the PCV, or do you just want?
They're the same can. They're the same can.
Okay.
And you don't want to vent your PCV?
I don't run a vent. I wouldn't run a vent. Okay. No. Some people run vents. It depends on how much vacuum you have, how much sucking you're doing. You know, if you want to do a lot of sucking, sometimes you need to add a vent so that you don't make too much vacuum in the crankcase. If you had a vacuum pump or something like that, and a lot of alcohol or methanol drag cars are going to just have vacuum pumps on them. So in cases like that, you might have a filter so that it limits how much vacuum you can draw on the crankcase. You don't want 15 pounds of vacuum on the crankcase. You just want a few pounds of vacuum on the crankcase. And that's more of an engine discussion, and I'm not here to tell you, this is the optimal amount of vacuum to keep on a crankcase to keep the rings seated on the bottom side of the lands and stuff like that. But there's power to be had just by sucking on the crankcase. You'll make just a parasitic amount of power improvement just by putting some vacuum on a crankcase. 2 pounds of vacuum on a crankcase versus 2 pounds of pressure in a crankcase, you're going to see it on a dyno. It's going to be small, but you're going to see it. You're going to be able to see it if you do a good test.
We did some, if you don't mind.
Go right ahead.
So we did some ring testing on different types of gas ported rings, and seeing how that affected it. And the same thing there, you could see with that crankcase pressure going up, just the power dropping off. And at this top end here, the other thing you got going for you, or going against you, is when you're lifting, you're at super high RPM. And the higher the RPM, the harder it is for that ring to seal. So the amount of blow-by you'll get as you release there and you got full vacuum and stuff is exceptional. It's an exceptional amount, so anything you can do to address that is definitely going to help.
And you'll see two types of techniques at the top end. You'll see the guys that just lift and leave it in gear, a lot of smoke generally, and you'll see the guys that click it into neutral and brake, a lot less smoke normally. Unless there's a PCV. If there's a PCV in there, that RPM, that D-cell RPM, is a lot of vacuum in the intake manifold. So you can actually use that vacuum in the intake manifold. Maybe 20 pounds of vacuum in the intake manifold on a D-cell. So you could use that on the catch can, and then you could D-cell in gear and not have smoke, but your rod bolts are not going to be happy with you. So I don't normally advocate D-celling in gear on drag cars because we don't build them. We build the rod to go in compression. And on turbo cars, we got residual exhaust pressure in the chamber. So even on the exhaust stroke, while we're pulling the piston down, with pistons coming down, we have some residual pressure there that helps us not pull on the rod bolts quite the same way you would on an NA car. So I usually don't like to decel in gear if I can help it on drag motors, But good question. Anybody else want to talk about oil leak? Okay, well then, if somebody wants to hand me another topic, or if somebody has a question, then we can cover something else.
Where do you get a decent PCV valve at? Seems like others always had issues with just doing regular boost that could leak back into the intake. Maybe I
Use just like a check valve?
You can, yeah, a PCV valve is a check valve. Yeah, so you don't have to use a factory PCV valve. You could go to the Summit catalog and you get a 1-inch diameter sprung check valve. Okay?
Oh, okay.
You don't have to use the factory one that just wedges in there between the valve cover and the.
Yeah,
you can use.
Even for I was just a smaller setup, it's become inadequate, not enough.
Yes, see, because the diameter, just the flow capacity of that PCV.
Yeah.
Even though you are sucking on it with a lot of D-cell vacuum from the intake manifold, it's like a straw.
Yeah.
You can't evacuate all that pressure that's building up fast enough. So you might want to change to like a 1/2 inch or 3/4 inch tube for that. Really let that vacuum suck on that crankcase. That'll keep all your D-cell turbo leaking from ever happening. Another kind of tech support question I get a lot of times at the shop is a guy that blows something up and he just can't believe that it blew up. I just got this and I just did this and I just did that and it blew up. And okay, like, can you believe it blew up? Well, yes, of course I can believe it blew up. You know, it glows red. It spins 150,000 RPM and it contains 50 pounds of pressure, of air pressure. Yeah, it's like a grenade. You know, it's almost more surprising that they don't blow up. You know, that one did blow up. You know. You look at these things wrong sometimes and you can cause a problem. A lack of oil pressure when you launch, you know, not everybody's not using dry sumps, you know, so you know, you got 4.5, 5 quarts of oil in a 4G63, for example. You sit there on the two-step for 2 seconds, what 5,000, 5,500 RPM. Well, now 1.5 quarts in the valve cover. And it ain't coming down till the end of the pass because you're having blow-by that's going into the bottom of the motor, coming up the oil return tubes, keeping that 4.5 in the valve cover. Okay, so now you got 3.5 quarts in the pan, you got 1.5 in the valve cover. We're 1 and 2 seconds into this pass so far, and we haven't even launched the car yet. Now you launch the car with 1 G of forward acceleration and 1 G of downward acceleration from gravity. Now your oil, your 3.5 quarts is left in the pan, is now at a 45-degree angle in the bottom of that pan. Where's the pickup at? Below that or above that or what? You know, who knows? Okay, so sometimes if you have high frequency data logging on your oil pressure, you'll look at your first 60 feet and it's good, and then all of a sudden the oil pressure trace starts doing this. You know, if you're sampling on a high enough frequency, if you're sampling like once a second or something, you're just getting one data point. You might see one little low one, and then the rest you might catch the bubbles going by and get one low reading, or you might not see any of them, and it might just look like your oil pressure's fine when it wasn't. You just didn't look often enough. You know, if you told a kid not to eat the candy and you only look over there once every minute to see if he's eating candy, you might totally miss him eating the candy. Okay, you know, but if you stare at the sucker, nope, don't eat, nope. You know, so that's data sampling is important. You know, how quick am I going to check that value of that sensor? And when you're done a data log oil pressure, generally you're trying to data log because you want to know if you're losing oil pressure or not when you're launching. So moving the pickup tube to the back of the pan, covering the front of the pickup tube so only the back of the pickup tube is open. You know, so that when the pickup tube, imagine it looks like a little matchbox, you know, rectangle, and it's got a wire screen on the bottom of it. Well, if the oil is like this, and the front of the pickup tube is in the air, and the back part of it is submerged, well, we're just going to suck the oil through the screen, and we're going to suck air through the front part of the pickup tube. Because a lot of times you'll see people put caps on the front side of the pickup tube so it only can pick up oil from the back. You know, there's ways of dealing with that. Maybe make the pan a little deeper, extend the tube a little further down so it's harder for the oil to get up on the back side of the motor. But if you don't have a dry sump and you're not, you know, just picking up oil from the tank where you've collected it and put it in the tank, and I'm going to pick the oil up from that to go to the pump, then you have a chance of picking up air bubbles. You have a chance of picking up a lot of foamy oil on the launch, and a lot of times you'll see it when they launch. So journal bearing turbochargers on really high G launch cars, you see this problem come up. You'll see scorched thrust bearings a lot of times, just because of that. And it feels pretty good. And, you know, a little bit of in and out play. It's like, yeah, the thrust bearing is scorched up. You know, some bubbles got into it. You know, you're like, what are your 60 foots? I'm running a 1.5. You know, I got these, you know, 8-inch slicks all the way around. I run a 1.5 60 foot. And I was like, yeah, I think I know you're badass, but you broke it. So you know, so journal bearings have that weakness, that inherent weakness. Ball bearing, if you put 10 drops of oil into a ball bearing turbo once every 10 seconds, it's going to make it. It's going to make it around the block. It's going to make it home. Just intermittent oiling is not a problem for a ball bearing. Journal bearing has to be oiled all the time. You ever see that air hockey game? People don't play that as much anymore, but it used to be really popular when I was a kid. Air hockey, you turn the fan on, the table has tiny little holes all over the table, and the puck slides across the top of the table, but it doesn't really because it doesn't touch the table. It's sitting on the air. So the puck is designed with a little concave on the bottom of it, so the air comes in and fills up the little chamber underneath the puck, and the puck just slides across effortlessly. But if you're going to go score a goal and you whack that puck, and it's right then, you could instantly turn the air off at the same time, then it wouldn't be an air cushion underneath the puck anymore. It would hit the table and it would start to have friction. And if it was going the same speed as the thrust bearing was, it would catch on fire. The whole thing would just catch on fire right then.
That's why they're brass.
Turbochargers are, you go 130,000 RPM. Well, the thrust bearing might be 16 millimeter in diameter, but that's still 150,000 RPM, and the radius might only be 8 millimeter. But it's still a lot of surface speed there. You still have 100,000 feet per second kind of surface speed, just on a thrust bearing. Somebody check me on that. That's going to be a YouTube video. Somebody do the math on that. 16 millimeter, 8 millimeter radius, 150,000 RPM. What's the surface speed? So it's a lot. It's enough to have friction there that'll start a fire. When you take these things apart sometimes, when this has happened to it, everything will look great inside the turbocharger. The journal bearings look great. There's no heat on the piston rings, no heat damage anywhere. It's just a thrust bearing looked like somebody took a torch to it. And this is characteristic of when you have a lack of oil pressure for just a moment, just really momentary. Like if you took the car and put it at a 45-degree angle and just put it on the two-step. The car was designed with gravity in mind, and the car was not designed with 1 or 2 G's of forward acceleration in mind. So GTRs, of course, it's a lot later. It's 20 years later for GTRs, and they were designed with this in mind. They do have some internal scavenging and some stages of pump and sucking, and there's journal bearing turbochargers, but there's a solution for this problem designed into the system, so you don't see it being a problem on GTRs. This was not a big thing in 1990 for 205 tires. That we were going to pull this sort of acceleration forces and be able to put all the oil on the back of the motor. So ball bearing turbochargers are great for that. Journal bearing turbochargers are going to have inherent weakness in that area. So, got a couple more minutes if anybody had another question.
Ball bearings have a short lifespan.
So should I run coil lines on my FP bolt-on turbo? If it's, let's go with both.
Say it again?
Should I run coil lines on my FP bolt-on turbo?
Yeah, totally. Because that turbo is designed to be have the same service interval as a factory turbo. There's no reason you shouldn't be able to run that turbo for 30 or 60,000 miles. Okay, what's going to kill that turbocharger is a homicide, not a natural death. So that turbocharger is going to die of a lubrication induced failure, a foreign object induced failure. You're going to have killed the oil pump. Particulates are going to start moving around the oil system. You're not going to know about the oil pump right away because you don't have an oil pump failure button on your dashboard. Okay, so it's going to start grinding itself into an oblivion. There's particles going everywhere. That's going to kill a turbocharger. So these are the things that are going to kill a turbocharger. But those are homicides. That's not a natural death. For a natural death would be what you're talking about, and you can prevent that or extend that lifespan by having those coolant lines on that. Is it going to die this year or next year because you didn't put the coil lines on it? Lines on it? No, it won't. It won't. And if you're not putting many street miles on it, you're just you trailer it everywhere. You only driving you do is from the pits to the staging lanes, down the track, and back to the pits. The water, the coolant lines is not going to change anything for you. You had a question, sir?
I was saying, don't ball bearing turbos have a short lifespan?
They shouldn't.
No.
They shouldn't. But a lot of ball bearing turbochargers are non-water cooled. Okay. Like a matter of fact, all the precision whole line of ball bearing turbochargers are not water cooled. And when you put a restrictor in the oil feed to a ball bearing turbocharger, what are you doing? What's the restriction mean? You're cutting down on how much oil's going there. So you're not doing any cooling via the oil flow. Journal bearing turbocharger, you're running so much oil through there that the oil's actually doing some cooling. It's a cooling function happening. You can measure the temperature and a half of the oil going into the turbo versus the oil coming out of the turbo. And a 16G making 35 pounds a minute, you got an 80 or 90 degree temperature difference through the turbo. The oil gets hot going through the turbo. It's accepting heat out of the turbo and taking it down at the tailpipe or down the drain tube. So, but on a ball bearing, you don't. So when the turbo gets really hot, you get a lot of heat soak into the turbocharger. There's no oil volume going through it. What does that mean? That's like that bed of coals, and you're going to run across it. Okay, barefoot. and everybody's doing it, and you're like, wow, it works great, and you start hitting across there, and then your mom texts you, and you stop in the middle to read your mom's text. Okay, it's a delta T issue. So if that oil goes into that really hot turbocharger and it doesn't move in and move back out, it just camps there, it's gonna burn. Just like bacon grease on a stove. It's just gonna turn into black, crinkly stuff. That's gonna cut down the lifespan of the bearings. Because that hard carbon is a particulate damage item. It's not supposed to be there. Balls have to run over it and crunch it up. So that damages the races. It doesn't damage the balls so much because they're ceramic, but the races, especially the inner race, gets damaged from that. So I think that's about my time, guys. Thanks a bunch for listening, and thanks for the good questions. And
I just want to acknowledge that you are the master of analogies.
Thank you. Everybody's got a text from their mom, right? I didn't check that out. What's that? Thank you. Take it back. All right. Well, you guys are DS. Who's a DSMer? Who doesn't have an FP race manifold? Okay, they're $100 off. So I just wanted to remind everybody, I got manifolds with me for the DSM and for the EVO iron ones, and they're $100 off. So if you don't have a basic bare bones a nice manifold for your DSM, I brought some with me. So
We got Evo ones too.
EVO ones and DSM. They're not super sexy and fancy like Matt's.
The hell
So,
not.
don't expect the last 5% of performance out of them, but for a lot of people they do okay. So then I guess that's about it. Thanks everybody.
Thank you.